Hello, my name is Charlotte Liddon and I am a PhD student in the Department of Geography at the University of Liverpool. This presentation will introduce and discuss how computer models can be used to simulate flood inundation in river, coastal and estuarine environments. The presentation will focus on one such computer model called LISFLOOD and how it can be used as a research tool to improve our understanding of flood inundation, prediction and risk assessment. Computational coastal flood inundation models can be used to simulate the movement of water over high-resolution topographic data of the land surface. They can provide detailed assessment of flood risk for an area. These numerical models represent tides, waves, currents and surges in coastal waters by solving equations that underlie their hydrodynamic processes. They calculate rates of change of water depth and extent across time and space that will result from different combinations of variables. For example, different meteorological conditions, different tidal conditions, and varying coastal defence systems. The models are developed using observational data, which allows them to be validated. Once validated, a model can be used to simulate a number of what-if scenarios, including sea level rise, storm surges, and sea defence failure. They can provide a forecast of what could happen in the future. LISFLOOD is a two-dimensional flood inundation model which simulates local variations in the depth and extent of water level and depth averaged flow velocity. The outputs from LISFLOOD can be used to illustrate inundation as a series of maps and scenarios. The model has been successfully used in the coastal environment. For example, to estimate a 1 in 1,000 year flood event with varying degrees of sea level rise in the Thames estuary, or flood extent in Fleetwood, northwest England, due to a 1 in 250 year storm tide with sea level rise, river flow, wave overtopping, and a combination of these variables. These examples show how LISFLOOD can be used in a sensitivity study context to simulate a number of different conditions the coastal zone may experience. The increasing availability of high-resolution topographic data acquired using airborne remote sensing, for example, light detection and ranging data, allows for more accurate representation of flood inundation. LISFLOOD operates over a raster or square grid of LiDAR data to predict the dynamic propagation of flood waves. Water moves across the grid from a user-defined boundary over floodplains. LISFLOOD simulates floodplain inundation in 2 dimensions by solving the shallow water equations which describe water flow. The model assumes that the flow between 2 of the grid cells within the domain is a function of the surface height difference of the 2 cells and gravity. The flowchart on this slide shows each input dataset that is required to run LISFLOOD. Time-varying boundary conditions define the hydrodynamic and meteorological inputs which will operate across the model grid. Each of the time-varying boundary conditions can be changed to simulate a range of scenarios. For example, progressively more severe storm surges can be simulated, or increasing sea levels over time. The digital elevation model dictates how and where the water will move across the grid, and sea defences can be digitised into the model domain. A uniform or cell-by-cell floodplain friction coefficient is applied to the model grid to simulate friction values of the land which the water flows across. A uniform flow velocity can also be applied at the model boundary to determine how fast the water moves into the model domain. LISFLOOD has been used to investigate the viability of tidal lagoons in the North Wirral coastline, similar to the lagoon proposed at Swansea Bay. Tidal lagoons use the large tidal range in the UK to produce clean, green, renewable energy, which is entirely predictable. In addition to this, tidal lagoons can act as a sea wall to protect coastal communities from future flood risk and thus reduce the cost of damage in these areas. This project looked at the feasibility and benefits of tidal lagoons as mitigation and adaptation strategies to future sea level rise projections. These maps show the depth and extent of flood inundation in the North Wirral model domain with no tidal lagoon present, simulated using LISFLOOD. The outputs from the model are presented as a series of inundation maps. The model shows flood inundation as a result of a 1 in 200 year storm tide under present-day mean sea level, 0.72 metres and 0.98 metres sea level rise. These sea level rise estimates are taken from the 95th percentile of the Intergovernmental Panel on Climate Change projections. The maps show that as sea level rises, there is a greater depth and extent of inundation along the south coast of the Mersey estuary. This is the northerlymost channel on the map. This is Stanlow and Ellesmere Port, areas of power infrastructure, including an oil refinery. This is an area that it would be important to protect against future sea level rise and storm surges. The same sea level rise scenarios will run as those seen in the previous slide, but an 11-metre seawall has been digitised into the model grid. This can be seen as a curved semicircle along the northwest coast of the Wirral. This represents our tidal lagoon. This map shows the difference in depth and extent of inundation for each sea level rise scenario with and without a tidal lagoon. The orange areas on the south coast of the Mersey, Stanlow and Ellesmere Port, show that the presence of a tidal lagoon on the North Wirral coast mitigates flood risk under future sea level rise scenarios. The reduced flood risk in this area following the construction of a tidal lagoon could be because the structure narrows the main tidal channel into the Mersey. This limits the magnitude of tidal streams up the Mersey estuary. Coastal zones worldwide are at risk of flood inundation as a result of sea level rise and extreme conditions such as storm surges and wave overtopping. There is a need to plan for, adapt to and mitigate against such risks. Coastal inundation models can help with this. LISFLOOD is a two-dimensional flood inundation model which can be used to simulate water depth and extent in coastal, estuarine and fluvial environments under a range of tidal and meteorological conditions.